We will continue talking about page replacement algorithms. This video is going to focus on least recently used LRU algorithm to replace pages that are not available in the physical memory. So we continue using the same page reference string as we did in the previous two algorithms for optimal and FIFO page replacement. And see how this can benefit us in terms of page faults. We, we definitely cannot do as good as optimal, which was 9 page faults, and we cannot do as bad, hopefully, as FIFO, which resulted in 15 page faults. So let's see how we do with this one. So we have the string, a page reference string at the top, followed by the contents of each page frame. So frame 1, 2, 3, for example, page 7 goes here. Then we are requesting for page 0, which can occupy this frame, empty frame. Page 1, it can still take up this spot. So page 1 goes in the third frame here. But when we try to bring in page 2, we are going to have to look at the least recently used. So right now the recently used would have been page 1, but the least recently used would have been page 7. So we take page 7 out and we bring in page 2. So this algorithm looks behind. So it looks at the usage so far. So it looks at the history, but it does not look in the future, which could still be a problem. So page 7 has been referenced. Page 7 hasn't been referenced over here for the longest time compared to 0 and 1. So that's the one that goes out, and we bring in page 2. When we try to access page 0, it's there, so we don't have a page fault. That's why we have an empty spot here. And when we try to access page 3, we are going to have to replace either 1, 0, or 2. Well, we recently accessed 2, so we don't throw that out. We recently accessed 0 right here, so we don't throw that out. So we have to throw out the last one, which is 1, which is the longest time. Reference hasn't been referenced for the longest time. So we throw out 1 and bring in 3. And we follow that for the entire sequence of 20 references. And this will have fewer than FIFO page faults, but we definitely have more than the optimal because we are not looking in the future. So for example, if we look at the page reference for 4, we brought in 4 to replace 2, but because we did not have the ability to look in the future, we didn't have that knowledge. We threw out 2 here and then we accessed 2 right here. So it was close to the optimal algorithm. The LRU's performance is close to optimal, but it still doesn't do as good because it doesn't recognize, for example, over here that 2 was about to be needed in the future. The complete algorithm for 20 page references results in 12 page faults. So it's sort of between the two ends. The best was optimal so far, and the worst was FIFO so far. So 12 is right, sort of right in the middle. So that's recently used algorithm, and we implement this using a stack or a counter. So let's see how we do that in just a little bit. Right now we are just summarizing the LRU least recently used. So what are some advantages and disadvantages of using in this algorithm? The advantages are this is almost as good as the optimal algorithm. So we are at least having the knowledge, so at least we are using the history, even though we don't use the future. We do not have the ability, we do not have the knowledge of the future. Bellidy's anomaly, which means that the number of page faults increase with the number of frames for a certain page string, that is not going to happen for LRU because it uses a stack-based or a counter-based it's a stack-based algorithm. So no Bellidy's anomaly for LRU. And it is widely used for, this particular algorithm is used for cache usage as well. The disadvantages are that it is going to be more complicated and more expensive compared to the FIFO algorithm, which was very simple. So we would probably need to keep a timestamp. We would probably need to maintain a stack, and the operating system needs to do that to determine the order in which the page was used. So the time of last use needs to be monitored. So it may require substantial hardware assistance, which makes this algorithm a little bit more expensive than FIFO. So let's take a look at the LRU's implementation and approach 1. So this approach is based on counters. So what we can do is we can add a timestamp field to page tables. So for each page table index, we can have a timestamp field, and that timestamp tells us how frequently the page was accessed and the order in which it was accessed. And we can add a counter register to the processor so that the counter can be incremented on every page reference. So the moment the processor asks or tries to access a page, we can increment that counter. So the higher the value of the counter, that means that there is a lot of value. So there is it's being referenced very recently and a lot. So by monitoring that counter value, we can throw away the page with the least counter value. When a page is referenced, every time we have a page reference, we can copy the counter that the counter register that is maintained by the processor over to the timestamp field for that particular page, so that we can keep updating the timestamp field in the page table with respect to the counter that's maintained close to the processor. And the victim page, the page that we try to replace, will have the smallest timestamp. So the counter doesn't get incremented too many times, which means that it's not being referenced too many times. So out of all the pages that we need to replace, the page which has the least timestamp can be kicked out. So we certainly have a lot of implementation overhead over here. For example, we need to maintain a counter close to the processor. We need to have an additional timestamp entry in the page table, which again is part of the main memory. So the operating system needs to monitor all that, which means that every page reference we need to copy over the contents and update the timestamp field. So there is certainly a lot of overhead involved over here. Let's see an alternate implementation approach, LRU implementation number 2. So over here we look at a stack. Instead of keeping counters, we are going to manage a stack of page numbers. So we have the same, let's say we have a different reference string here. We are accessing page 4, 7, 0, and so on. And when we access page 2, we are going to maintain a stack. The stack is shown over here, which contains the pages that are currently in the physical memory, and page 2 is right at the top. So the top of the stack is what suggests that that page has been recently used. So whichever page we use the most recently, we simply take that page in that frame and put it at the top of this stack. And by doing that, we are going to have that page which has not been used in a while trickle down and becomes the bottom of the page. So whenever we feel the need to replace a page, we will kick out the page that is at the bottom. So we remove things from the bottom of the stack and we push new things to the top of the stack. Either we can do that replacement in two possible options. One is when we reference it, for example over here, or when we bring in a new page, it goes to the top of the stack because it's the most recently accessed page. So that's the stack at the position A. So that stack at A looks like this. And it has 2 at the top because 2 was accessed recently, and it should have 1 right next to it because it was the next recently used. and so on. And this is essentially monitoring that the stack is at A. So the next reference is to page 7, and as you can see, 7 is present in the memory here, so it needs to come to the top, and 2 needs to go one level down at that particular location. So at stack at time B is going to have, it earlier had 210, 7 needs to come in to the top, so we are going to move 210 down and then bring in 7 to the top of the stack. Over here, note that there was no need to kick anything out, so we didn't kick out 4. We had 7 in available to us, so we just accessed it. The implementation overhead over here is a little bit less compared to the previous counter implementation. Over here, we still need to maintain a stack. So the operating system needs to maintain a stack, and every time we have an access, it needs to push things to the top of the stack. So there is implementation overhead, not as much as the previous implementation. So let's try to look at an approximate least recently used algorithm because we have implementation overheads, severe implementation overheads in implementation 1 and 2. So let's try to approximate some aspects. So we do this by having additional reference bits. So let's say we have a reference bit for each page, and it is set by the hardware to 1 whenever page is referenced. So if we reference a page, we set this reference bit to 1, and because this algorithm depends on least recently used, from time to time we are going to have to reset it to 0 so that we signify that it is not being used for a while. So after a certain time interval, we can set or reset this reference bit to 0 to indicate that the page has not been referenced in quite a while. But as you can see that this reference bit is just 1 bit, and it is talking about pages being referenced or not being referenced in a while. However, it doesn't tell you the order in which the pages were referenced, and also it doesn't tell you the frequency of that page reference. So we are going to need a few more bits to tell us the order and the frequency of usage, and we do this by maintaining a history byte field, so 8 bits telling us the history for each entry in the page table. So let's see how we do this. At timed intervals, usually about every 100 milliseconds, we are going to transfer the control to the operating system so that it updates the 8 bits in the history field based on the reference bits. Let's see how this works. So for each page table entry, the history byte is shifted right by 1 bit, and when we shift things to the right, we open up the most significant bit slot. So we are going to set that high order bit or the most significant bit equal to the reference bit for that page. So the reference bit could be a 1, could be a 0, and it will be a 1 if it has been referenced recently. It will be a 0 if it has not been referenced in a while. We will set that particular reference bit as our most significant bit of the history field. And by doing this, we are monitoring the least recently used aspect of a particular page. And we will see that in an example in just a bit. And certainly we cannot leave this to the reference bit to 1 for the entire time. We are going to have to reset that reference bit at that time interval. So we do that to all pages so that we can again do this in a cycle so that we keep an order and frequency monitoring going. So those regular timed intervals are about 100 milliseconds. Every 100 milliseconds that happens, it's going to shift right by 1. So that means that the history byte, the 8 bits in the history byte field, go right by 1, and we simply copy the reference bit of that page to the higher order bit. And by doing this, we are keeping track of the last 8 time periods, the history of the last 8 time periods. So for example, if the history byte is all zeros, that means that the page hasn't been used in the previous 8 time periods. So every time we accessed it, we copied over the reference bit, we moved things to the right, and we brought in the reference bit to the most significant slot, and it looks like it's all zeros, which means that it has not been referenced in a while, at least in the last 8 time periods. If you see all ones, that means that the page, that particular page for which this history byte corresponds to, that page has been accessed at least once in each of the last 8 time periods. Note that this does not mean that it has been accessed 8 times. We could access it over here, and whenever we access, the reference bit becomes a 1, and by moving things to the right and updating the most significant bit, we may have all the 8 bits go to 1 if the regular intervals, the time intervals, are much longer than the time at which we had the change in the reference bit. So we have to use the term at least once in the last 8 time periods to signify what all the 8 ones mean. Now, if we compare a string with the most significant bit being a 1 and the most significant bit being a 0, clearly this field, this first history byte, that page has been more recently used, because this suggests that the reference bit was 1 for that 8th time period, but that is 0 for that 8th time period. So even though there are more ones over here, we look at the position. We look at the position being 1. So if we can interpret these history byte as a 8-bit unsigned integer, then the page with the lowest integer number, for example, the one on the right here, is the least recently used. So whenever we try to replace a page, we are going to do that to the least recently used, or the page with the least history byte value. And at the page fault, the page with the lowest history byte is the victim, and that's what will be replaced. We can also approximate LRU by using what we call a second chance FIFO. So FIFO was based on only one chance, right? So whenever things were the first in was thrown away the first. But if we give 2 chances before we throw away a page, that is called a second chance FIFO, and we'll see how that works. We'll continue to use a reference bit for each page. We are going to set this using the hardware to 1 whenever page is referenced. However, in the previous approximate LRU scheme, we were using a timer, and whenever that timer expires, we were resetting that reference bit of all pages to be a 0. In this case, we are not going to use a timer. Instead, we are going to use the FIFO algorithm to make the reference bit 0. Let's see how that works. So we implement this using a circular queue, and you can see that circular queue over here. Some reference bits are 0 in red, and in yellow you see 2 frames with pages 7 and 1 with reference bits 1 and 1. And we are going to implement this scheme as a circular queue. The algorithm will be maintained by a routine called check clock. So we are going to check the page pointed by the clock hand. So for example, if the clock hand is pointing to this particular frame in which there is page 3 and the reference bit is 0, if the reference bit is 0, R is 0 here, we are going to evict that page. So we are going to replay. The new page takes the position of this particular slot, this particular frame. The new page is inserted in its place, and we advance the clock hand, say clockwise, to the next frame. So if now the clock hand is pointing to a frame in which there is a page 7, but the reference bit is a 1. So what should we do if the reference bit is a 1? Well, if the reference bit is a 1, we are going to give it a second chance. We are going to reset that bit to a 0. We are going to advance the clock hand. We are not going to replace it because we are giving it a second chance. We are going to advance the clock hand to the next page, the next frame here, which has page 0 and R is 0. So this will go out in this case. And we continue to go through that routine of check clock. So this is your second chance FIFO. We are giving 2 chances before we throw away a page. So this is another approximate LRU scheme that we see in implementation very often. All right. This completes the lectures on page replacement algorithms. You guys are ready for the activity.